Hi everyone, welcome back. We're going to go through the remaining questions from Daman High, H2 Math Prelim 2022, Paper 1. So that will be questions 7 to 11. Alright, so question 7 is sequences and series. Right. So, find in terms of n and x an expression for the following sum. R equals to 0 to n of x plus 3 to the power of r divided by 4 to the power of r plus 1. Now you might actually realize that this is a geometric progression of some sort. So this can be rewritten in a certain way. I shall rewrite this with power r minus 1. And how I'm going to do that is I'm actually going to change this index to r equals to 1, and then the top will become n plus 1. And I will factor out a quarter, and this will give me x plus 3 divided by 4. And this will be the common ratio, r minus 1. Here I can apply the sum of GP formula, which will give me quarter of 1 minus x plus 3 over 4 to the power of n plus 1 divided by 1 minus x plus 3 over 4. Which can be simplified a little bit. If I multiply in the quarter here, I'll just get 1 minus x plus 3 divided by 4 divided by n plus 1 divided by 1 minus x. And I think that's good enough because there's only 2 marks. They do not really need us to simplify any further than this. (7a) part 2. Give a reason why the infinite series converges. Okay. When x equals to negative 5, we have the sum r equals to 0 to n of x plus 3 divided by r divided by 4r plus 1. In fact, this x is minus 5, right? This is 1 minus, if you put in minus 5 here, you get negative half, and divide by 1 minus negative half, which is 3 over 2. Oh no, sorry. It's 1 minus negative 5, which is 6, okay? As n tends to infinity, sum r equals to 0 to n of minus 5 plus 3 power r 4r plus 1. This actually tends to 1 over 6 because because negative half less than 1 implies that negative half n plus 1 tends to 0 as n tends to infinity, right? Convergent geometric series. So the answer will be 1 over 6. For part B, we are given the formula for the sum of squares. Find in terms of k this sum. We're going to find the sum from r equals to 6 to 2k of r 3r minus 2. Now, we always want to start with the index of 1, right? So here's what's going to happen. We expand this, we get 3r squared minus 2r. I'm going to factor out the constant, so I'll get 3 times the sum of r equals to 1 to 2k of r squared minus 2 times the sum of r equals to 1 to k 2k of r, and then this subtract the sum from r equals to 1 to 5 of r 3r minus 2, And the latter, this last term here, you can actually just use your GC to find the answer. So, applying the formula, we substitute n for 2k, and we will get, the 3 will also cancel out the 6 here, so actually we'll just be left with k times 2k plus 1 times 4k plus 1. Apply the sum of AP here. This will be 2k times 2k plus 1 divided by 2 multiplied by 2 outside, so this is minus 2k plus 1 divided by 2, the 2 here cancels out, so this is minus 2k times 2k plus 1 minus 135, and this can further be simplified because this is 2k plus 1, that's 2k plus 1, so this is 2k and this is k times 4k plus 1, 4k plus 1 and k. Alright, so that should be k, 2k plus 1, 4k minus 1, minus 135. Okay? Yeah. Then 7b part 2. Evaluate the following sum. So we're going to go r equals to 10 of up to 66 of r minus 4 times 3r minus 14. Now there's always some kind of a index replacement for this kind of question. If you notice, you replace r by r plus 4, then this is actually equivalent to the sum r equals to 6 to 62 of r times 3r minus 2. Since when you replace r by r plus 4, this becomes 3r plus 12, minus 14 plus 12 is minus 2. Then you can apply the result from 7b part 1, where it was summed up to 2k, right? K equals to 31. So this is equals to 31 times 63 times 123 minus 135. And this is exactly equals to 240,084. Of course, you can use your GC to help you check the answer. That's that. Question 8, functions. We have a function f defined by f of x equals to ln x squared plus 2x plus 1. And we also have g here, which has some properties. We'll get to that in a bit. So 8a, we're going to sketch y equals to f of x. Now, of course, you can use your GC to perform this sketch. It's not a standard graph, so please use a GC. There will actually be a vertical asymptote, y equals to x equals to 0, and the curve will increase somewhat. And it seems to just go to infinity basically. X equals to 0 is an asymptote, x and y. This is the origin. For x less than 0, it actually turns out to be always negative, but there is a turning point. It just seems to decrease without any bounds. Okay. Okay. So there's a turning point here, and this turning point is actually important for the later part. So I will label its coordinates, even though the question didn't ask for it. And in fact, you can actually find the coordinates to exactly be -1 and +1. Okay, and you can use your GC to check this. Oh, sorry, -1 also. Okay. And for what it's worth, I can also label this 0.405. Okay? Yeah. So this is the graph of y equals to f of x. What is the graph of y equals to g of x? Well, it has exactly one asymptote, which is y equals to 0, and it is continuous decreasing. G0 is -1. Okay? What could that look like? continuous decreasing and asymptote is y equals to 0. So this line here, this is the y equals to 0, x-axis, right? If it is a decreasing function and g0 is -1, that means that it must be increasing before that, right? It must be increasing when we head to the left side, right? So, actually no, how should I explain this? It seems that we cannot get like a function that's going in the right side direction. But we know that asymptote is what happens when we study the behavior of y when x tends to infinity or negative infinity. It turns out that it's possible that if x tends to negative infinity, y tends to 0, because what happens is that this will be a graph that looks something like that. Okay, this is -1, and this is y equals to 0. It's possible for the asymptote to be on this side, right? Yeah, and this will be the graph of y equals to g of x. Okay. Explain why the composite function fg exists and find the range. Okay. Now, when explaining why a composite function exists, you always check the domains and range. So fg means that we check the range of g, check that it's a subset of the domain of f. So the range of g is -infinity to 0, excluding, and the domain of f is, well, is everything except 0, right? Therefore, the range of g is a subset of the domain of f, and therefore fg exists. What is the range of fg? You start from the domain of g, which is use the range of g as a restricted domain of f essentially. So domain of g is all real numbers. You apply g, you get the range of g, which is -infinity to 0, and then you apply f from here. -infinity to 0 of f, you'll see that actually it's always negative, right? So the range here will be -infinity and 1, -1, sorry. And this is a closed interval, right? Because it's a turning point, it's not excluded. Okay, so that will be the range of fg. Given that fg is this thing, find an expression for g of x. Okay. Now the problem here is that we can actually see from the graph that f is obviously not 1, 1. There's no inverse function. So how can we solve for g of x? Well, it turns out that intuitively speaking, we can try and guess and check our way to find the function of g of x. Okay? We see that it's like the composite function has a polynomial part and an exponential part. So this could look like an exponential function, right? Of some sort. And it turns out that if we put exponential inside, we will get an exponential part as well as the linear part from here. So we try and guess and check an expression. Most likely g is just some sort of very basic e power x kind of function, right? So let's just make a guess. So what I'm going to do is actually find fg of x explicitly. So we put in ln g of x squared plus 2g of x plus 1, and this is 14x plus 1 minus 2e7x, right? So my guess is I compare the 2g of x to the 2e7x, right? So my guess is, let me just highlight this. I'm making a guess between these two. Guess is that g of x is minus e to the power of 7x. And in fact, e to the power of 0 is is 1, right? So of course this makes sense. Oh, sorry. I think it's I think it's yeah, this. Okay. So check ln of negative e power 7x squared minus 2e7x plus 1, and this is e power 14x, right? Plus 1 minus 2 e power 7x, and ln e something is just the thing itself, so 14x plus 1 minus 2e7x, okay, which is correct. So actually the g of x is negative e power 7x, okay? D. If the domain of f is further restricted to x greater than k, state least value k for which the function f inverse exists, okay? If we check the graph, you'll see that clearly if x is greater than 0, then it's 1, 1, right? So we will write that down. So that would be k equals to 0. f1, verify that this is 3. So this is ln 1 square plus 2, 1 plus 1, which is 0 plus 2 plus 1, which is 3. Okay, easy. And use this result to find the gradient of the tangent to the curve y equals to f inverse. Okay, that's interesting. What I'm actually going to do, right, is I'm going to have to find the derivative of f, right, first. So f prime x, because now we know that x is positive itself, so we can ignore any of the thing about this being an absolute value. So we can actually find this to be 2 ln x, so this is 2 over x plus 2, since x is greater than 0, okay? And then f prime of 1 is 4, okay? 2 plus 2 equals 4. If we look back at our graph, so 1 will be somewhere here. The gradient here is actually going to be 4 somehow, okay? But then we draw the inverse function. We draw like this one will be a bit steeper actually. So let me look something like that. No, actually like that. Yeah. Then your x looks like that. Then what's going to happen is that your inverse function is going to look something like this. What is the gradient at this point? So this is the gradient here is 4, for example. What is the gradient here? Well, the point is 3, 1, right? So it seems to be a reflection. So you will see that the gradient here is steep while the gradient here is narrow, right? But it's still positive. It seems that the gradient will just be the reciprocal also, right? So therefore, gradient of f minus 1 at x equals to 3 will be 1 over 4. Alright? And you can probably prove this rigorously, because tangent inverse of a number plus the tangent inverse of its reciprocal will be pi over 2. And yeah, you can go and work it out, but I don't think it's necessary lah. Okay? Question 9 is vector geometry. Okay, we have a point and a line, and they both contain in the plane P1. So of course it's good to rewrite your Cartesian equation of a plane into the vector equation form. So x minus 2 over 2 equals to y minus 4 over 3, and z equals to 6. So let there be a parameter gamma. Gamma equals to x minus 2 over 2. Then we can actually obtain the vector equation in terms of gamma, right? So 2 gamma plus 2, so x is 2 gamma plus 2, y is 3 gamma plus 4, and z is still 6 without gamma. So L has equation. So the equation of line in P1 is R equals to there's a fixed point 246 plus gamma 230, right? And then gamma is a real parameter. And we have a plane P2 written in the parametric form. But what I want is a normal vector to P2 later. So we'll get the scalar product form later. But first of all, let's see. Line of intersection between B1 and B2. When you want to find line of intersection, you always like the Cartesian, right? So let's find a Cartesian equation of P1. Scalar product first. So oh yes, to find we'll find a vector that is parallel to P1. Which is the fixed point on the plane 246 minus A, right? The position vector of A. So 246 minus 4, 4 and 0. And this is 6, this is 6, 0, 0. No, 6, okay? Which is 6 times 101. So equation of P1 is R dot, what is the, sorry, we need to find the perpendicular vector first. Normal to P1 will be direction vector of the line 230 cross the vector that is parallel 101, and we get let's see, this is 3 minus 2 and minus 3, I believe. Let me check. Yeah. Okay. So therefore, equation P1 is R dot 3, negative 2, negative 3, which is pick any point. So we'll just pick the point minus 440, which is on the plane. Dot 3, negative 2, negative 3. And this is yeah, minus 20. Okay. So you therefore have an equation that you can convert to Cartesian form easily. Minus 3x plus 2y plus 3z equals to positive 20, right? This will be the Cartesian equation. And the other plane has a Cartesian equation. So normal to P2 is going to be 1, 0, negative 1 cross 0, 1, 1. And this is 1, negative 1, and 1. Okay. So equation P2 will be R dot 1, negative 1, 1. And 246 is also on that plane. You'll actually notice that 246 is on both planes, right? Which is quite interesting. So 246 dot 1 minus 1, 1, which is 4. So you get x minus y plus z equals 4. Okay. This is, let me call this equation 1. And let me call this equation 2. Then use GC for 1 and 2. And you will get the expression right. You actually get x equals to negative 28 plus 5t, y equals to minus 32 plus 60, and z equals to t. So the vector equation of the line at intersection Well, we know that actually 2, 4, 6 lies on both planes, right? So we can actually choose 2, 4, 6 to be our fixed point, plus t, and then we pick the direction vector 5, 6, 1. Also, why did I write z equals to 6? I meant to write z equals to t. And t, 5, 6, 1. So yes, it is parallel to 5, 6, 1. Okay. Yeah. 9 part B, determine the acute angle between P1 and P2. Okay, very standard. It is simply cosine inverse of the dot product of the two normal vectors, then divide by each of the individual magnitudes. So that will be 3 minus 2 minus 3 and 1 minus 1, 1, right? Okay. 3 minus 2 minus 3 dot 1 minus 1, 1, and then divide by the individual magnitudes. Okay, which is 3, 2, okay, so this is 2 over, and then this is 11, okay, root 33, okay, cosine inverse 2 over root 33, actually no, I think it's 36, 66, yeah, 66, sorry, okay, 2 over root 66, and when you find angle for vectors, usually you put an answer in degrees. This turns out to be 75.7 degrees. Okay. 1 dp for angles. Okay. Find the position vector of the foot of perpendicular. Also standard. Let F be the foot of perpendicular from A to P2. So what we do is we want to have AF, which can be expressed as OF minus OA. And because OF lies on P2, I can actually write this as wait, let me actually write this as OF minus 440 first. Okay. And this must be a scalar multiple of the normal vector to P2, which is 1 minus 1 and 1. Right or not? Okay. And also, OF dot 1 minus 1, 1, because OF must lie on the plane, right? So therefore, it must also be equals to 4, since the plane is R dot 1 minus 1, 1 equals to 4. Sorry. Oh yes, because this has to be equals to minus 440 dot 1 minus 1, 1 plus 3 alpha. Okay, because OF dot, because this is AF dot this vector, because AF is parallel to it, right? So when you dot two parallel vectors, you get some square magnitude. So you get the magnitude of this squared, which is 3, so 3 alpha. So therefore OF dot this must be equals to OA plus AF. So you get 3 alpha plus the OA dot with the vector itself. So you will get 3 alpha minus 8 equals to 4. Therefore alpha equals to 4 also. Okay. So therefore OF will be minus 440 plus AF, which is 4 minus 4 and 4. So this is 0, 0, 4. Is it? Yeah. Okay. For part D, the plane pi 3 has the equation ax plus 3y plus 2z equals to b, where a and b are real numbers. Find the values so that all 3 points have a common line of intersection. Well, there's already one line of intersection, and that line contains a certain point. If we can find a point that lies on that line, we need to just simply sub in that point into this plane, and then it will pass through that point also. In fact, it will pass through the same point of intersection. So we'll sub in 2, 4, 6. Let x equals to 2, y equals to 4, z equals to 6, since 2, 4, 6 lies on P1 and P2, right? You'll get 2a plus 6z equals to b minus 12. Oh, sorry, 2a plus, no, sorry. Let me just write out the full thing. 2a plus 12 equals to b. So therefore, 2b minus 2a equals to 24. And what else is there? We need another piece of information. Oh yes, the normal vector will be a3, 2. And this normal vector is perpendicular to this vector is parallel to the intersection, and that intersection line is 5, 6, 1. Okay, which is actually no. I think it's no, they are perpendicular. Sorry. So this we dot and we check this to be 0. So we get 5a, 18 and 20, right? Okay. Plus 20 being equals to 0. So a is negative 4 and b is 16. Okay, cool. Sorry, because the intersection line is perpendicular to this vector. Okay, yeah. Okay. Differential equation, question 10. We have dv dt equals to 5 minus 0.2 v squared, which in fact you will notice actually this is 1/5 of 25 minus v squared, and yeah. So let's separate the variables. We will get integral of 5 divided by 25 minus v squared dv equals to integral of 1 dt. So you will get 5, well, you can use partial fractions or you can use the MF26 formula. You will get half ln 5 plus v, mod 5 plus v divided by 5 minus v equals to t plus c. And when, okay, which is when t equals to, it moves from rest originally, so when t equals to 0, v is also equals to 0. So ln 5 divided by 5 is ln 1, which is 0. So therefore you have 0 equals to 0 plus c. C is also 0. So it turns out that t is actually half ln 5 plus v, mod 5 plus v divided by 5 minus v. But we can actually simplify this a bit more. This is actually just half ln of, without the modulus, 5 plus v divided by 5 minus v. Okay? And the reason for this is because you can analyze the differential equation. It will be, if your v is greater than 5, then this will be 0. Then this will be negative, and the velocity will decrease until it gets to back to 0, which is exactly when v is exactly 5. On the contrary, if your v is less than 5, then your dv dt is increasing, so your v will continue to increase. This is actually what we call a stable equilibrium. So therefore, we can actually conclude that 0 less than or equals to 0 is less than or equals to v less than or equals to 5. Okay, I know division by 0 is undefined, but you get the idea lah. Okay, so this will be t in terms of v. Describe how the velocity of object varies with time. Okay, I think there are two requirements with this part. You need to describe that when v is less than, you need to describe what happens when v is less than 5 and when v is close to 5. When v is less than 5, when as t increases, v increases, because you have t in terms of v, right? As t increases, so how does this increase? V increases also, right? But you need to see that it's actually decreasing at a decreasing rate. Okay? And this is one part. The other part is long-term behavior. As t tends to infinity, so this tends to infinity when v tends to 5, right? Yeah. So this will be the thing that I think you need to say 5 meters per second. Is it? Yeah. Okay. And if you want to add on a bit, if v greater than 5, dv dt is less than 0, so v will decrease until dv dt equals to 0 at v equals to 5. So I think this last part is optional, and I will say that this is what we call a stable equilibrium. If you take physics, you'll probably know what this is. If you don't, then never mind. It doesn't really matter. Okay, 10 part C, okay, integrate 0 to m of v dt. So of course we need to find an expression for v in terms of t now. We have t in terms of v, which is the other way around. So let's start by writing the equation again. T equals to half ln of 5 plus v, 5 minus v, right? Okay. So we'll start by raising e to the power of 2t equals to 5 plus v divided by 5 minus v, which is minus 1 plus 10 over 5 minus v. So we get 5 minus v divided by 10 equals to, so we bring the 1 over and then we take the reciprocal, so 1 over 1 plus e power 2t, and then from here we make v the subject. So v is 5 minus 10 over 1 plus e power 2t, and in fact I shall rewrite this as 5 minus 10 e power negative 2t e power negative 2t plus 1. I multiply the top and bottom by e power negative 2t, and that is because of the fact that I will be integrating this later. So I will integrate. So distance will be integral of 0 to m of 5 minus 10 e minus 2t divided by e minus 2t plus 1 dt. You'll notice that the derivative of the bottom is negative 2 of this, so I actually get a f prime x fx kind of integral. So this actually gives me 5t. So I bring the minus 2, I have 5 left, so I add 5 ln e minus 2t plus 1. And I do not need a modulus here because this is always positive. So we're going to go from 0 to m. So this is 5m plus 5 ln e minus 2m plus 1. And then this is 0 and 0 when you have 0 inside, because ln 1 is 0. And how do I combine this into a single term? Well, I can actually write m as ln e to the power of m, right? Okay, so this is actually e minus 2m plus 1. Okay, I might be missing a 2 actually. I think this is... Oh, there might actually be something here, because if I put 0, right? Oh, this is, when you put here 0, you actually get 5 ln 2, so my bad. 5 ln 2, and then minus 5 ln 2. And then of course you can combine the logs together. So you multiply throughout, you get e power m and e power negative m. So this is 5 ln e power m plus e power negative m divided by 2. Okay, so that will be what you wanted to show. And interestingly, this is what we call the hyperbolic cosine function. So it's interesting that it pops up here in this DE. Although if you want to know what the hyperbolic trigo functions are, you can go look online. For A levels, I don't think you need to know what specifically it's for, but you do use it to model the dynamics and kinematics sometimes. Okay, so now we have a differentiation application question, it looks like. I think it is. So we have this cone thing, this IV drip bag. Fluid is to be delivered. Okay, 50 cm cube hour. Determine the value of H in the volume of IV fluid left when H is decreasing at rate 1.21. So 11 part A. So what is the rate of decrease in the cylinder? The cylinder has a constant surface area, right? So the height decrease will also be constant. The rate of decrease of height in the cylinder will be the rate of decrease in volume, which is flowing out at 50. Okay, so 50 divided by 16 pi. And you can actually evaluate this to be 0.995, which is less than 1.21. Therefore, we prove that actually decrease 1.21 cm per second must be in the cone, right? So we can actually ignore the cylinder already. So let V be the volume of the fluid in the cone. Okay. By similar triangles, and also let R be the radius of the surface area, surface level. Then by similar triangles, we can actually consider H to be the height of the cone already, so we don't need to worry about the cylinder anymore. So we will get R over H, and this is actually 4 divided by 4, because the radius here is 4 and the height here is also 4, so there's actually 1. So R and H are actually the same quantity, so therefore you get V equals to pi over 3R cubed. Okay, dV dr will be pi r square, and you can use this to solve for the value of R. Actually, I can write it as pi h square. How about that? How about I consider... Yeah, I should probably consider h actually, but never mind. I can also write, since h equals to r, I can also write dv dh equals to pi h square also. Okay, so dv dt, or dh dt rather, we use the chain rule. This will be dv dh, no, dh dv times dv dt, which is this the rate of decrease, so we get 50 over pi h square. Then we let the h dt equals to 1.21. You solve for h. Okay. Pi h square over 50 is 1 over 1.21. You'll actually get h equals to 3.6267 to 5 SF. Okay? And what is the volume at this point? You can sub this into the thing. Pi over 3 this thing cube, which is 49.955, which is 50. Okay? So this is 3.63 cm, this is 50.0 cm cube. Okay? And then all these 3 SF are. Can? Okay, cool. So now we have a different diagram. Once the IV fluid enters the body, we have this resistance kind of thing. Total resistance is the sum of the resistance of the two paths. So for 11 part B, we need to show this thing. 11 part B. Okay. So let R1 be the let R1 be the resistance of this one, the AD cylinder, right? So R1, we apply the formula given to us. It will be mu, and the viscosity of the blood will be the same for both blood vessels. That's the assumption, right? So we use the formula mu. The length will be is the resistance above AB. Okay, so R1 equals to mu AB divided by R14, right? And how do you get AB? Well, AB is actually, this is M and this is K. So this is the opposite and this is the adjacent, right? So I want the adjacent from the opposite. So I take K cotangent theta. Okay. So mu AD minus BD divided by R14. This is mu of M minus K cotangent theta divided by R14. Okay. And then R2 is a similar principle. We apply, I want to find the length of BC. So mu BC, mu BC divided by R2 power 4. And BC can be written as, this is the opposite we want the hypotenuse. So this is K cosecant, mu K cosecant actually. Mu K cosecant theta divided by R2 power 4. So the total resistance is R1 plus R2. Okay, and then you can of course factor out the mu, and then from there follow through lah. M minus K cotangent theta divided by R1 power 4 plus K cosecant theta divided by R2 power 4. Okay. As theta varies, show that cosine theta equals to R2 power 4, R1 power 4 when it's stationary. We found that RT equals to mu of M minus K cotangent theta divided by R1 power 4 plus K cosecant theta divided by R2 power 4. Okay. And to find stationary value, we differentiate with respect to theta, the RT d theta. This is, okay, so we'll get the mu will stay outside. When we differentiate M R1 power 4, this will be gone. So we just differentiate the cotangent. Derivative cotangent is negative cosecant square theta. So you'll get positive one here. So you get mu K cosecant square theta. And then when you have cosecant theta, differentiate this, you'll get negative cosecant theta cotangent theta. So you'll get minus, this one is divided by R1 power 4. Then minus mu K cosecant theta cotangent theta. Okay, divide by R2 power 4. And what I'm going to do is I'm going to factor out mu K cosecant square theta. Okay, so this will give me 1 over R1 power 4. I have only one cosecant here, so this actually becomes sine. Cotangent times sine is cosine, so minus cosine theta divided by R2 power 4. When the RT d theta equals to 0, we know that actually cosecant square theta is not 0, right? So therefore, this must be 0. So 1 over R power 4 must be cosine theta divided by R2 power 4, from which we can immediately deduce the value of cosine theta. Cosine theta is R2 power 4, this is R1, divided by R1 power 4. Okay. And lastly, we need to prove that this is a least resistance. Now, when we have unknown constant, usually we do a second derivative test. The 2RT d theta square. Okay, so this is, we need to differentiate this thing. So we'll keep the cosecant theta first. So we get mu K cosecant theta and differentiate that thing. This 1 over R1 power 4 is gone. We differentiate negative cosine, you get positive sine. So you will get sine theta divided by R1 power 4, or is it R2 power 4, I think. Then we keep the other term and we differentiate cosecant square. This is cosecant square. When you differentiate cosecant square, you bring down the 2, differentiate cosecant, you will get negative cosecant cotangent. But that was already, so you're minus 2 mu K cosecant square theta, cotangent theta, then you bring down that whatever thing. Yeah, 1 over r1 power 4 minus 1 over cosine theta divided by r2 power 4. Then you sub in theta when cosine theta equals to r2 power 4 divided by r1 power 4. You'll notice that this entire thing becomes 0. So you get the 2rt d theta square just equals to mu k cosecant theta. Yeah, cosecant theta, because cosecant square times sine is cosecant, divided by r2 power 4. Okay. Then I make a simple justification. Since theta is acute, cosecant theta will be greater than 0. Therefore, d2rt d theta square is also greater than 0, and therefore is a minimum, right? Yeah. Okay. So that'll be all for Diamond High, paper 1. My next video should be an E-math paper, because I need to go through a couple E-math paper 1s for my juniors. We're going to take the O-level E-math paper in, 5 days? So hopefully I get that up later today or tomorrow. I'll see you guys around.